Welcome, everyone. For those of you who don't know me, my name is Ren, and on behalf of the Ore Deposits Hub, thank you for joining us for this lecture on the formation of IOA and IOCG mineral deposits. It's a case study out of Laco, Chile. I have the pleasure of introducing our speaker today, Adam Simon, who hails from the University of Michigan, where he's a professor of earth and environmental sciences. And it's clear he's passionate about responsible sourcing of natural resources for a sustainable future. His current research group focuses on improving genetic models for mineral deposit formation, and in today's talk, Adam will be presenting new data from the enigmatic Laco IOA deposit in northern Chile, and other IOA and IOCG deposits in the Chilean iron belt that are not consistent with existing models. So I'll give the floor over to him, and let's listen in on what's sure to be an exciting talk on a new genetic model to explain these deposits. Please, Adam.
Great, thank you. So I'm going to share my screen and just confirm you can see what I see, which is a title slide. We're
Yes.
good? Okay.
Yeah.
So first let me start off by saying I'm going to focus today's talk on El Laco, which is an enigmatic deposit in northern Chile that has plagued geologists since it was first described in a paper by Charles Park almost 60 years ago. And at the very end of the talk, I'm going to give a little bit of lip service to the relationship between iron oxide-apatite deposits and iron oxide copper gold deposits, but I'm not going to go into the details of how we think they're connected. I think I'll suggest that for a future talk. I want to first acknowledge a large group of people who have been instrumental in helping us with this research over the last 8 years. So Martin Reich and Fernanda Barra, who are both professors at the University of Chile, we started this new collaboration in 2013. And over the last 7 to 8 years, we've been fortunate to have a lot of really fantastic graduate students here in the middle row at both the University of Michigan and the University of Chile who have helped us with the projects. And I want to make sure that I give much of the sweat equity credit to these 3 graduate students, Jose Tomas Oval, who's a PhD student at the University of Chile, Nikita La Cruz and Tristan Childress, who finished their PhDs at the University of Michigan last year. They have put a lot of the sweat equity into our work at El Laco over the last several years. And then to the comment about not taking screenshots, a lot of the data that I'm going to present today is either already published in this top paper here, for which Jose Tomas is the first author, and it's open access, so anybody can download that from the web. And then the second papers here at the bottom, which are both in press with economic geology, and first authors are Nikita and Tristan. So everything that I'm going to present today is either already published or will be published. And if anybody would like copies of the papers, just please send me an email and I'm happy to get that to you.
Okay.
So let's just start off, and then the other comment I'll make here is that I'm going to present sort of a broad brush overview of El Laco. In a 1 hour time frame. I don't have enough time to go into all the subtle details and nuance of the deposit. So just bear with me and take in the big picture, which is important to set up the study that we've done over the last few years. So here I'll focus in on South America, and then the inset here in red is blown up, and you can see Chile, Bolivia, Argentina. So here's the border between those 3 countries. And the El Laco volcanic complex is shown here in the blue triangle. It's associated with the northwest-southeast trending Calama-Olocopado-El Toro lineament, which is responsible for the alignment of Neogene Quaternary volcanic activity in the region. The El Laco volcanic complex itself is the product of a complex volcanic history developed from the Miocene to the Pliocene. And El Laco, the ore deposits that I'll talk about today, are Plio-Pleistocene. The volcanic complex is punctuated by several volcanic events, including explosive eruptions that led to stratovolcano collapse, resurgent volcanic activity, fissural emissions, and late stages of intense hydrothermal activity. And these events are also correlated temporally with this cluster of andesitic to dacitic volcanic structures that comprise numerous northwest trending fissural emission centers that you see regionally around the El Laco volcanic complex. If we zoom in on the El Laco volcanic complex itself, I just want to point out that there are 6 ore bodies that outcrop at the El Laco volcanic complex. Pico Laco is the central volcanic dome, And then we've got 1, 2, 3, 4, 5, 6 ore bodies that outcrop around the central Pico Laco central part of the volcanic complex. And this is a cross section from Frutos and Oyarzun in 1974. This is the central Pico Laco here. And then I just want to highlight that proximal to the central peak, we've got what have been interpreted as magnetite lava flows that outcrop here on the surface on both sides of Pico Laco. And you can see that the magnetite lava flows, or what have been interpreted to be magnetite lava flows, are connected at depth to magnetite ore bodies that extend below the surface. The magnetite ore bodies at the surface, and I'll show you some photographs of this, are on average 90+% modal magnetite with minor pyroxene and often what I would describe as very scarce apatite. Laco is almost misdescribed in the sense that it's not really an iron oxide apatite deposit. It's effectively a magnetite deposit that has a small amount of apatite among the ore bodies. The magnetite ore bodies are intercalated with flows of andesites and daceites at the surface. And when you visit Laco, here's a photograph of me at Laco a few years ago. In the background is the Laco volcanic complex. This is a photograph taken from the guard station. And all I want you to picture here is that this is massive magnetite everywhere that you can see in the background of the photograph. The total estimated resources are approximately 734 million tons, and that grades about 50% iron. So there's about 375 million tons of iron among the 6 ore bodies that outcrop at the surface and penetrate to depth. And almost 90+% of those ore bodies, that iron is contained within the mineral magnetite. When you walk around on the surface, here's a photograph of Tristan Childress a few years ago when we visited. When you walk around on the surface, if you've ever visited Hawaii or a similar area that has vesicular basaltic lava flows, it is amazing how strikingly similar the ore bodies are when they outcrop on the surface to those basaltic lava flows. We're standing here on the Laco Norte ore body, and I just want you to take this in for a second, because if I didn't tell you that Tristan is standing on top of ore that is 90+% magnetite, you would never think that visually. You would automatically think this is a mafic flow of some form. When you walk around Laco Norte and the other ore bodies on the surface, they all have similar structures. They're characterized by lava-like textures, and those lava-like textures characterize the upper almost 100 meters of each of the ore bodies that we've studied in drill core. And then at depths beyond 80, 90, 100 meters, the ore bodies transition into magnetite breccias that extend to depths of at least 200 meters. Among the things that really intrigued us when we visited Laco the first time is when you look at some of the outcrops here that have been mined, you can see within these outcrops these lighter colored enclaves. And these are altered andesite enclaves hosted within massive magnetite. And when you zoom in, it's here you can clearly see the alteration. So some of these are large blocks, or you might think of them as bombs, but I just want you to keep this in mind because this is something that seems to be unique to Laco in terms of having these large andesitic or altered andesitic enclaves within the massive magnetite ore bodies. When you look at them up close, on the left-hand side is a field photograph about the size of my hand. And then on the right, you can see my fingers for scale. This is one of those samples that has been cut open. And what I want to highlight here is the vesicular nature of the interface between the magnetite and the andesite enclave. And then within the andesite enclave, there are also magnetite clasts. So it's not that you have pure andesite and pure magnetite. You can see that there's intermixing where we've got these magnetite clasts within the altered andesite. And then on the bottom of the screen here, I've got a backscattered electron image with a scale bar of probably 1,000 microns, because I can't see it on my screen, where you can see magnetite here dominates the sample, and then it is intergrown with diopside. Among the things also at Laco that has intrigued people is the presence of these vesicle pipes. So here's one, probably one of my favorite vesicle pipes. because it has the shape of a heart. So if you ever question whether or not God loves geologists, this tells you that she does. And when you look at these vesicle pipes, they are lined with beautiful euhedral magnetite growing from the walls of the pipe in towards the center of the pipe, which everybody watching the talk today can probably right away determine that this represents growth of magnetite from a vapor or a vapor-like fluid that filled these cavities during the formation of the ore body. So here's a question I have for the audience. When you see papers written about El Laco, the word lava is often used. And in fact, when Charles Park wrote his seminal paper in the early 60s, he wrote the word lava in quotation marks because he wasn't convinced that it represented the true lava, but that it had characteristics similar to lavas. So when you look at these three photographs, if you were to be asked which one of these is El Laco and which one of these is Hawaii, which would you pick? Here are the answers. So the top left, this is vesicular basaltic lava flow from Hawaii. And we know now extremely well by experimental and theoretical studies how these vesicle pipes form. And it's by degassing after the lava flow vents to the surface. And I just want you to keep in mind the similarities between these textural characteristics at Hawaii and El Laco on the right and left and bottom of the screen. So when Charles Park visited, he was a consultant for Bethlehem Steel Company in the late 1950s. Charles Park, who was not this guy, Charles Park spent his career as an economic geologist at Stanford University. And he visited as a consultant for Bethlehem Steel. And when he saw the massive magnetite ore bodies, they apparently reminded him of basaltic lava flows like we see on Hawaii that I show a video of on the right. And when he saw the vesicles, they reminded him of, even at the time, what we knew was the cause of those vesicles in basaltic lava flows and lava flows of other compositions. So Charles Park, in his paper, had the word flow in quotation marks. And again, his paper stimulated what has now been almost 60 years of trying to understand how the El Laco ore body formed. How do you have massive magnetite on the scale of tens to hundreds of meters that outcrops on the Earth's surface and has all of these beautifully preserved vesicles within the massive magnetite ore bodies? How can you explain that? So there are two fundamentally different hypotheses that have been proposed to explain the El Laco ore bodies. One is referred to as the hydrothermal replacement model, and there are lots of papers by these authors here. And I'll just give you the quick skinny about the hydrothermal replacement model. What it invokes is complete metasomatic replacement on an atom for atom basis of pre-existing andesitic and dacitic lava flows. So step one is eruption of silicate lava flows, and step two is atom for atom replacement of all the silicate minerals within those lava flows by the mineral magnetite, meaning that we have a fluid that percolates into the system and completely removes all of the pyroxenes, all of the plagioclase, all of the amphibole, all silicate phases, and precipitates in their place magnetite, preserving all of the original textures. Now, there are different fluid sources proposed for this model that include basinal brines from lacustrine evaporites and also magmatic hydrothermal fluids. So this is hypothesis one. The second hypothesis is liquid immiscibility. And on the left-hand side, I've got a schematic from a paper by Tornos et al. In 2016. And liquid immiscibility has also been described in papers going back decades by these authors here that I'm circling. And the hypothesis here is that at some depth below the El Laco volcanic complex, there was a primary parent silicate melt that during cooling and decompression unmixed into coexisting iron phosphorus rich melt and silica rich melt. So that would allow unmixing to produce an iron rich melt that could crystallize to form the magnetite rich ore bodies, and a conjugate coexisting high silica melt that would form perhaps rhyolites or high silica dacites. One of the challenges with this model is that there is no evidence in the field for the conjugate silica rich melts. And one of the things that it requires, as discussed in this paper, is that during unmixing, water in the original parent silicate melt must preferentially partition into the immiscible iron phosphorus rich melt. And that's because the iron phosphorus rich melt is more dense than the conjugate high silica melt. And so under gravity and density, the iron rich melt should sink and the silica rich melt, which should retain the water, would float. But the model for liquid immiscibility actually proposes the reverse. It proposes that water enters preferentially the iron rich melt, which allows the iron rich melt to ascend because the addition of water lowers its bulk density, and the silica rich melt would not have water, and so it would remain at depth. So one of the things that we observed in all of the papers written about El Laco over the last 50 plus years is that all of the studies were based on collection of samples only at the surface. And a majority of the studies are based only on samples collected here at Laco Sur, and you can come up with a variety of explanations for that. One is that's the closest ore body to the road, and you're at about 6,000 meters elevation, maybe about 5,000 meters elevation. So by the time you get to Laco Sur, you're winded and you just want to get back to your car and drive back down to lower elevation. But nonetheless, one of the things we noticed is all the studies were based on surface. So what we've done over the last few years is we've collected samples from all of the ore bodies, and we've studied drill core here highlighted in the yellow stars. So we've looked at samples in 5 drill core from multiple ore bodies, which, as best we can tell, gives us the first set of samples from depth in the ore bodies. And here, I'm going to walk you now through the data that we've put together over the last few years. So first, I'm going to show you the textures of magnetite from the surface down to about 200 meters. And I'm going to build this out progressively. So here's a BSE image, a scale bar is 200 microns, of euhedral altered and porous, what we call magnetite S, from a surface sample. And magnetite S is pervasively altered and replaced by hematite and goethite along grain boundaries, fractures, and pores. Magnetite S is characterized by abundant microporosity and pervasive replacement of hematite and goethite. And in the center here, I've got the depth. So magnetite S is from a surface sample. And on the right-hand side, I've got the concentration of titanium. Magnetite S has very little titanium. If we go a little further, so now we're down at here about 60 meters, you can see that now we've got a second magnetite type, which we label magnetite Z. And magnetite Z is a weakly to moderately oxidized magnetite characterized by hematite formation along rims or through fractures. And magnetite Z, we observe it to be aggregates of pristine, mostly euhedral crystals. And one of the things I want to highlight here is, as we go from magnetite S at the surface to magnetite Z about 50 to 60 meters below the surface, notice that the titanium concentration increases. If we go a little bit further, now we're about 75 meters below the surface. Now what we find is a third and fourth type of magnetite, which we label magnetite X, which occurs as pristine microcrystalline cores that are replaced by magnetite Y via dissolution reprecipitation processes. And magnetite Y, these overgrowths on magnetite X, are characterized by an oscillatory texture where we have alternating inclusion-rich or trace element enriched and inclusion-poor trace element depleted bands. And notice the concentration of titanium increases. If we continue even further, now we get what's shown over here on the right-hand side, what we call magnetite alpha and magnetite beta at the bottom of the deposit. And now we're in what we call the deep zone, which comprises a breccia body with andesite fragments replaced by fine-grained diopside within a magnetite diopside matrix. Magnetite beta, which I'm tracing over here at the bottom left, commonly occurs as coarse-grained euhedral crystals that contain inclusion-rich cores, and you can see that here, all of the black here within magnetite is the inclusion-rich core, surrounded here by inclusion-free rims. And then if we look at the deepest part of the section, we see magnetite alpha, which forms an aggregate of titano-magnetite crystals with well-developed ilmenite exsolution lamellae. And I think the most important part here is, to the best of our reading through all published papers, no one had ever identified magnetite alpha, which is characteristic of igneous magnetite that originally grew from a silicate melt as titanomagnetite, and during cooling and oxidation, that original titanomagnetite exsolves ilmenite along predefined crystallographic planes within magnetite. Now I'm going to show you some slides of the chemistry of magnetite from surface to depth. And this is to highlight all of the data that we've produced, plus data from the literature. And I'm showing you the data here on what has now become known as the aluminum manganese titanium vanadium discriminant diagram, where the y-axis is the sum of aluminum plus manganese and magnetite, and the x-axis is the sum of titanium plus vanadium and magnetite on log scales. The background here is, this is a line that separates magnetite from iron, titanium, vanadium deposits. So the discriminant diagram was built based on magnetite compositions in this field that I'm tracing here, where the magnetite crystallized from silicate melts. The field that I'm tracing out here is based on analyses of magnetite from porphyry ore deposits, which all plot within this field. The field here is based on analyses of magnetite from iron oxide copper gold deposits. This sort of large field up here are magnetite grains from skarn. Here we have magnetite grains from Corona deposits. And then over here, we've got banded iron formations. And what I want you to see here is, in yellow, we have the surface data from our study. And you can see that it pretty much spans all of the fields except for the iron, titanium, vanadium field. And then in blue, I've got magnetite chemistry from the drill core data in our study. And you can see that it spans the fields for porphyry and Corona, and also crosses over into the igneous iron, titanium, vanadium fields. Now, what's shown here with the circles are temperature estimates based on the original work of Patrick Nadal and Dupuy and Boudouin, who worked on these discriminant diagrams. But it's a busy diagram, and I'm going to focus your eyes on this one instead. So we've got the same aluminum, manganese, titanium, vanadium diagram. And now what I'm showing you are the drill core data in the background. All of the drill core data are in these blue circles. And then we've got all of the data here from the drill core. Magnetite S at the surface, low titanium, transitions to magnetite Z and Y and X, and beta and alpha with increasing depth. And what I want to focus your eyes on is this magnetite alpha, which is the magnetite that contains the exsolved ilmenite exsolution lamellae. All of those samples plot over here. Many of them plot in this so-called igneous field on the discriminant diagram, and some of them plot over here. And then as we get shallower in the drill core, here we have magnetite beta, which is shown here in the green diamonds. And then we have magnetite X and Y, and remember, magnetite X are the cores. Magnetite Y are those oscillatory zone magnetites that overgrow the cores. And then as we get even more shallow, we get to magnetite Z. And then the shallowest samples in the drill core are magnetite S. So what these data show us, if we look at the right-hand side of the slide, is that the trace element composition of magnetite systematically changes from depth to surface. I mentioned earlier only the titanium concentration, but what we can now see in the data is that all of the trace elements in magnetite are enriched in the deeper sections of the core and become systematically depleted as we move towards the surface. So there would be a trend, as I'm tracing out here, from deep to shallow. And I'll highlight, notice that trend beautifully mimics the same exact trend that we observe in magnetite from porphyry deposits around the world. And we know unequivocally that porphyry deposits are the result of a magmatic hydrothermal event that evolves from a silicate magma. So now I'll show you some other trace element plots. Here we've got vanadium versus titanium, and the top I've got the data for 3 of the ore bodies. The background fields here, everything that I'm tracing out here in the pinkish color would be magnetite globally from igneous systems, and then everything I'm tracing out here in the blue would be magnetite from purely hydrothermal systems, and then this overlap here is magnetite from magmatic hydrothermal systems. And again, what we can see is that all of the data either plot within the igneous field or they plot within this magmatic hydrothermal field, minus a few outliers. And then on the bottom, I've got the data for magnetite from the drill core. And again, what we can see is magnetite at depth is the most trace element rich. And as we get towards the surface, the trace element concentrations in magnetite decrease. Here I've got some multi-element or spider diagrams where magnetite is plotted relative to bulk continental crust. And I've got different fields plotted on each of these. This is after a paper that Sarah Dare wrote a few years ago, where I've got a field in the top panel for igneous rocks, magnetite from igneous rocks. The blue here in panel B is magnetite from low temperature hydrothermal systems. The purple here is magnetite from high temperature hydrothermal systems. And I'll focus your eye on the data again from Laco, where the magnetite minor and trace element compositions from surface samples overlap magnetite compositions from igneous intrusions and high temperature magmatic hydrothermal fluid. And we see the same thing when we look again at the drill core samples. So the magnetite from the drill core in each of the ore bodies reflects a systematic increase in trace element abundances, and the trace element abundances overlap or are comparable to trace element abundances in magnetite from igneous and magmatic hydrothermal systems. Here I'm plotting titanium, vanadium, and aluminum versus gallium. And all I want to draw your eye to here is that if we start here at the origin, these are shallow samples. And as I move my cursor from the origin, follow the red cursor or the laser pointer, we're going to deeper levels of the system. So what we see are clear trends in trace element abundances. Now I'm going to show you some temperature data. So there's a paper that was published earlier this year, or I think it might still be impressed by Keneal at UBC, who developed an empirical thermometer for magnetite crystallization. And I'd encourage you to read the details of that paper. But for my purpose, I just want you to know that this equation here that I'm circling allows you to calculate the temperature of crystallization of magnetite by using the concentration of magnesium, which is found to linearly be related to the temperature of magnetite crystallization. So you calculate the mole fraction of magnesium, which is the mole fraction of magnesium divided by the mole fraction of magnesium plus iron. And this equation allows you to calculate the temperature of magnetite crystallization. And I'm showing them here for simplicity against magnesium, but here's what I want you to see. For Laco Norte, one of the ore bodies that we studied, the temperatures of magnetite crystallization span the range from about 400 degrees to slightly in excess of 900 degrees. And they show this beautiful cooling trend where the most magnesium-rich magnetite crystallized at what we would think of as igneous-like temperatures, and then magnetite at Laco Norte just systematically shows lower temperatures, which are indicated by lower magnesium concentrations. And we see this in all of the ore bodies. So we have different amounts of data from each of the 6 ore bodies, or in this case, 7 ore bodies if we include Extensión Laco Sur. So here would be Laco Norte that I showed you on the previous slide. Here's Laco Sur, Extensión Laco Sur, Redatos Negros, San Vicente Alto, Cristales Grandes, and Pasos Blancos. And you can see they're all the same scale except for Laco Norte, which is more magnesium rich in some of the high temperature samples. But what I want you to see is that the temperatures span the range from magmatic temperatures through magmatic hydrothermal temperatures. And again, if you were looking at a porphyry system, you would say, well, duh, we know that porphyry systems evolve by cooling magmatic hydrothermal fluids. So you would almost predict this for porphyry systems. For El Laco, these are brand new data, and they indicate the systematic cooling of magnetite, where we have magnetite alpha, magnetite beta, magnetite X, magnetite Y, magnetite Z, and magnetite S. And so as a function from surface to depth, the temperatures tell us that the system was cooling. So now let me walk you through some stable isotope data. So I'm going to show you now data for oxygen isotopes. So the left side will become the delta 18O. Actually, let me take that back. The bottom axis here is the delta 18O ratio. And then the left-hand side, I'll build out with data from different papers. So I just want to highlight first, the bottom is delta 18O if you can't see it. I can't see it on my screen. And then I've got three fields here. The field at 0 represents the delta 18O composition of magnetite that would be in equilibrium with seawater. Then we have the pink field, which is the delta 18O composition of magnetite if it crystallized from a silicate melt or a magmatic hydrothermal fluid. So think intermediate to evolved silicate melts. And then the orange field here in the center of the pink field would be the delta 18O composition of magnetite crystallized from mid-ocean ridge basalts. And when we look at the data published in many papers, Tornos et al. 2016 is highlighted here, and then other data from Nystrom et al., Rhodes and Oreskes, what you can see is that a majority of the data, including data from our studies, so all of these data here that I'm showing in the colors are from our study. The X's are Rhodes and Oreskes, 1999, and then these data points over here are from Nystrom, 2008. What I'm showing here, or what the data reveal, is that all of the data from Rodatus negros plot within the field expected for magnetite that crystallizes from a silicate melt or a magmatic hydrothermal fluid evolved from a silicate melt. All of the data for Cristales Grandes similar. Most of the data for San Vicente Bajo, except for two. Two of the data points from Nystrom et al. For San Vicente Alto plot within the field, and then our data plus data from Rhodes and Oreskes do not plot within the field for magmatic hydrothermal oxygen isotopes. All of the data for Laco Sur plot within the field expected for magnetite that crystallizes from a silicate melt or a magmatic hydrothermal fluid. And then we see a range of data here for Laco Norte. Some of the data plot within the field for magmatic hydrothermal magnetite. And then we've got a spread of data out here to lighter isotope values. So now I'm going to show you a second set of stable isotope data. On the y-axis, we've got delta 56 iron, which is the ratio of iron 56 divided by iron 54 relative to a standard, plotted against delta 18O on the x-axis. And the box that I'm showing here is the box in which all magnetite that crystallizes from silicate melt or magmatic hydrothermal fluids should plot. Meaning that if you sample magnetite from an igneous rock and measure the iron and oxygen isotopes of that magnetite, they should plot here. And what we see with all of our data for El Laco is that most of the data plot within the box, but we have a few outliers. These boxes in yellow are San Vicente Alto, and then these two inverted triangles here are Laco Norte. And so the first thing that you should think here is that the majority of the data are consistent with magnetite that crystallized from a silicate melt or a magmatic hydrothermal fluid, but there are some outliers. We also measured hydrogen isotopes within magnetite, and the hydrogen isotopes is either the byproduct of meteoric alteration of magnetite or possibly from primary fluid inclusions trapped within magnetite as it crystallized. So here we've got delta D or delta 2H versus D18O. Here would be that magmatic hydrothermal box. And what you can see is that the samples define this trend, which we would think of as a degassing trend in a silicate magmatic hydrothermal system. But then we've got this excursion towards values that would be consistent with goethite in equilibrium with local modern oxygen and hydrogen isotopes of meteoric fluids. And so that's the best explanation for these outliers here in yellow and red, is the secondary alteration that we see in the system. And that's consistent, I'll point out, with the observation that in these samples, we see secondary goethite. And as the amount of goethite increases, the amount of water increases, and that's consistent with the hydrogen isotopes. So one of the things that we've done recently is we've started to do microtomography 3D imaging of magnetite samples. And I'll just show you here on the left is a video where we take a sample of magnetite and we put it into an instrument that uses X-rays to sample successive planes through the magnetite. So you get a 3D picture. And on the right, I'm going to play a video. And what you're looking at here, the majority of this is all magnetite. And everything that shows up to your eyes as dark is a lighter density or lower density fluid, or lighter, let me say lower density phase. And as I play through this, I just want to draw your eye to some parts of the tomographic image where you can see planes of fluid inclusions that are consistent, or you see planes of low density phase that are consistent with the entrapment of fluid inclusions during the growth of magnetite, or the entrapment of secondary fluid inclusions if the magnetite was fractured either during emplacement or subsequent to ore deposition. So we interpret some of the hydrogen isotopes that are consistent with a magmatic range for hydrogen isotopes to represent hydrogen that was sampled by us in fluid inclusions trapped in magnetite during growth from an originally magmatic hydrothermal fluid. And I said this a couple of slides ago, but just to point out, as the hydrogen isotopes become more negative, the x-axis here is the concentration of water in magnetite, so 0 water to 2.5 weight% water. Pure goethite has about 10 weight% water. And so these samples here, what you're looking at in terms of the hydrogen isotope composition and also the oxygen isotope composition is alteration of magnetite S by hematite and goethite. We've also recently measured oxygen-17 in these samples. So oxygen-17 is the least abundant of the 3 stable isotopes of magnetite. And the equation up here is how you calculate this value over here for cap delta 17. And the reason we have this little apostrophe or the prime here is because of the slope we're using, 5.305. So on this diagram, we've got cap delta 17 versus delta 18O oxygen. Here at 0 and 0 would be seawater. Here's the meteoric water line. And over here with the stars are data for Laco Norte, magnetite from Laco Norte. In the background in black and purple, or whatever that color is to you, are data from a recent paper in geology for magnetite from iron oxide-apatite deposits in Iran. This is the field for mantle, and this is the field for orthomagmatic magnetite. And this is the field for magnetite in equilibrium with seawater. We haven't 100% figured out what this vertical spread represents with respect to delta 18O. Again, this horizontal spread with D18O is consistent with all of the samples from El Laco having been, the oxygen in the magnetite having been sourced from a silicate magma. And I just want to highlight that the cap delta 17 here are also consistent with an orthomagmatic growth for magnetite. And these data seem to falsify the hypothesis, or they don't seem to falsify. These data falsify the hypothesis that the magnetite grew from a basinal brine. So the second hypothesis I mentioned at the beginning of the talk was liquid immiscibility. And we also use the oxygen isotope data from magnetite from El Laco to test the liquid immiscibility hypothesis. Because in this paper by Lester and colleagues in 2013, they experimentally demonstrated that during unmixing of a parental silicate melt into coexisting iron-rich melt and high silica melt, oxygen isotopes do not fractionate. And what that means is that after separation into coexisting silica-rich and iron-rich melts, the oxygen isotope abundances in both of those should effectively be the same. Well, what we observe at El Laco is that the andesites that host the ore bodies have oxygen isotope values in terms of delta 18O somewhere between 7.5 and 9. And this has been published in a number of papers. And all of the data for Laco, excluding the samples that are altered, all of the data for magnetite from Laco, they fit within this range from about +1 to +4.5, maybe +5. So using the experimental data from Lester in this paper, the oxygen isotope data should be the same in both the andesite host and the immiscible liquid if it's an iron-rich liquid that exsolved from a parent silicate liquid. And so the oxygen isotope data themselves falsify the liquid immiscibility hypothesis. We also then looked at additional data from Lester in a separate paper where he experimentally studied liquid immiscibility. And one of the things that Lester concluded is that in the parent silicate magma that is hypothesized to unmix into coexisting iron-rich and silica-rich liquid, if you add chlorine to that parent silicate magma, it eliminates immiscibility. And that's really important. So these are experimental data that tell us, or they don't tell us, they demonstrate that if you add chlorine to a silicate melt, you cannot get immiscible liquids forming during the evolution of that parent silicate melt. And we know from Laco that the system was chlorine rich. So this is a paper by Broman et al. In 1999. And what they report are the presence of hydrosaline melt inclusions in pyroxene crystals within the magnetite-rich ore bodies that have high homogenization temperatures that exceed 800 degrees. And then they also measured homogenization temperatures of fluid inclusions in apatite that homogenize at temperatures between about 600 and 250 degrees. And they conclude that the ore fluid at Laco was a very, this is all in quotation marks, a very complex aqueous fluid composition, and notice that it contained halide salts. So what that tells us is that the ore fluid at Laco was a chlorine-rich fluid, and we know from experiments that a chlorine-rich silicate melt does not unmix to produce an iron-rich liquid. So these data also falsify the liquid immiscibility hypothesis. And then the final challenge for the liquid immiscibility hypothesis is that the average ore composition at Laco is about 98% FeO and less than a weight percent P2O5. And this is a quote by a paper that Dick Naslund and Fernando Enriquez wrote for a field guide in 2004. And they proposed, you know, it's sort of funny here, that we should call these magnetitites if it wasn't so hard to pronounce. And this is what I mentioned earlier. Laco is not a magnetite-apatite ore body. Laco is a magnetite ore body. And the abundance of pyroxene, in this case diopside, significantly exceeds the abundance of apatite. And this is reflected here in the bulk composition, where you can see that Laco essentially contains a scarce amount of P2O5, consistent with almost no apatite. So this is a paper that was published last year, or 2018, by Tong Hao, and it's a great paper from an experimental perspective. I just want to highlight that it's been cited by a number of papers as evidence for liquid immiscibility at Laco. But one of the things to make sure you understand is the experiments contained no chlorine. So again, chlorine eliminates liquid immiscibility. There's no phosphorus in the deposit. And here we have what is otherwise a great laboratory study. And that laboratory study shows, if we look at the top left, that in order to have an immiscible liquid enriched in iron and phosphorus, you need to have as much as 40 weight percent P2O5. So this is 40 weight percent that the experiments require, and the system contains less than 1%. So the experiments are just completely not analogous to the natural systems. And until somebody does experiments that actually mimic the natural systems, these experiments really tell us nothing about the evolution of Laco. And then the second bit of data that the Hong et al., the Howe et al. Study published is water content within the immiscible iron-rich liquid. And remember I said that the liquid immiscibility hypothesis, it requires that the immiscible iron-rich liquid be water-rich to lower its bulk density so that it can ascend from the presumably water-poor high silica liquid that is then too viscous to ascend? Well, Tony, in a great study, measured the water content, and what they show here is that the silica-rich liquid is enriched in water, and the iron-rich liquid is not. So this is the exact opposite of papers written about liquid immiscibility, and it demonstrates that water preferentially partitions into the silica-rich melt, not the iron-rich melt. So the iron-rich liquid is in fact denser and sinks. It cannot buoyantly ascend. So what do we have when we look at all of the data? The data falsify liquid immiscibility. The data falsify the basinal brine hypothesis. The hydrogen, oxygen, and iron isotope data are consistent with a magmatic source reservoir. We have beautiful temperature trends that show that show crystallization of magnetite from a cooling ore fluid at temperatures in excess of 900 degrees down to temperatures of approximately 400 degrees. So we put all of these data together. And again, the first thing we did is we really interrogated the existing models to see whether or not all of these data, which we think are the largest and most comprehensive set of data for Laco ever produced, and also include the drill core data, which have never been part of any previous study. We could not explain our data with the existing models. So those initial hypotheses are falsified. So we developed a new model that explains the data, and it's just a model. So it's open to change, it's fluid, and we'd appreciate any advice people on the call today have that might help us better understand how our data can be explained. So the first part of our model is the emplacement of an intermediate silicate magma. Think of an andesite, and crystallization of magnetite within that andesite, and then settling of magnetite within the andesite. On the right-hand side over here are the results of modeling we did with the program MELTS, where we've got pressure versus temperature. And all I want you to see here is that in an andesitic melt, magnetite is commonly the liquidus phase, and magnetite therefore crystallizes before clinopyroxene and before plagioclase. And also for a water-rich andesitic melt, the melt reaches volatile saturation before crystallization of CPX or plage. So this we know is the reality for andesitic melts. We then developed, or let me give the acknowledgement here to Jose Tomas. Based on that cross-section I showed you earlier from Frutos and Oyarzón in the early 1970s, we developed a model that I'll walk through, and you can read the words here at the bottom over the next few slides. But our model, the model is as follows. That andesitic magma chamber is in place at shallow crustal levels here that I'm tracing out. And within that andesitic magma, we have the first four magnetite crystals, alpha and beta form. And remember, magnetite alpha is magnetite that now contains ilmenite exsolution lamellae, which require that to have originally been titanomagnetite that exsolved ilmenite during cooling and oxidation. So we have primary magnetite that forms in that andesite, and then we have a recharge event. And the recharge event is shown here by these pipes that are carrying more mafic or basaltic magma and underplating that basaltic magma below the andesitic magma chamber. And that underplating event, if the mafic magma here is volatile saturated, the volatile phase from the mafic magma will ascend buoyantly and enter the andesite magma chamber. And we know that that will stimulate or will drive the andesite to reach volatile saturation. And what you can see here are magnetite crystals. I'll blow it up. We've blown it up here on the right. Magnetite crystals that are wetted by that volatile phase. And I'll show you some experimental photomicrographs in a few slides that demonstrate this is the case. This happens. But that recharge event where we've got a volatile phase from the mafic magma that enters the andesite magma, stimulating volatile saturation of the andesite, magnetite crystals serve as the nuclei for a volatile phase exsolving from a silicate melt. So what we have then is we now have magnetite crystals that are wetted by a volatile phase. And that volatile phase because the vapor essentially is stuck to the magnetite. It allows magnetite grains to be floated up through either a crystal pore andesitic silicate magma, or they could possibly move up through fractures or tears that would be permeable conduits within the andesitic magma chamber. Now, importantly, the magmatic hydrothermal vapor phase would be chlorine rich. We know that chlorine preferentially partitions from the silicate melt into a vapor phase, and that allows the vapor phase to scavenge metals such as iron from the melt or the magma, in addition to other elements that strongly prefer to partition into the vapor phase. Think of sulfur, think of calcium, magnesium, think of silica, think of copper, gold. All of the elements that we know from studies of porphyry systems, both field studies and experimental studies. So now we've got the ascent of this vapor-rich magnetite fluid suspension, where it's carrying magnetite alpha and beta with it towards the surface. And remember, the crystal size of alpha and beta, they're very small, so they are easily buoyant within this magnetite fluid suspension. And that suspension allows magnetite to accumulate in the upper portions of the magma chamber here. And then if there is a collapse of the surface, that is a rapid decompression or a massive loss of pressure in the system. So the hydrostatic pressure here decreases instantaneously. And that would result in the formation of fissures. And then this episodic collapse would form large hydrothermal breccia bodies at depth, which would be characterized by a matrix of remobilized magnetite alpha and beta, which is what we see here in the studies of drill core from El Laco. Now, the iron-rich magmatic hydrothermal fluid, as it ascends and cools, we know from studies of magnetite solubility in magmatic hydrothermal fluids that as such a fluid cools from 800 to 600 to 400 degrees, we know that we will have magnetite crystallize, and the temperatures of magnetite solubility from experimental studies are consistent with the temperature of magnetite X crystallization, overgrown by magnetite Y, then the growth of magnetite Z, and then finally magnetite S, which grows from that magmatic hydrothermal ore fluid at and near the surface. So when you look in the literature for examples, these on the right-hand side and then the bottom are the textures we see. And if you can imagine, well, what the hell would a magnetite fluid suspension look like if it is emplaced and vents at the surface? You know, here I've got a video of froth flotation. So notice froth flotation and look at the similarity in the textures that we observe at El Laco, right? And what is froth flotation, right? This is a form of physical beneficiation where we've got a big flotation cell and we're bubbling air up from the bottom, and we've got bubbles of air that are wetted by some surfactant, a fat, a pine oil, and then the bubbles in this case are coated by a sulfide. But at El Laco, what we propose is that a similar process occurred where these would be magmatic hydrothermal fluid bubbles, chlorine rich, and they are effectively coated with grains of magnetite grown from silicate melt, the magnetite alpha and the magnetite beta. And at El Laco, what God does when she wants to intrigue us is she simply scraped this out on the surface. So this is what we're looking at. Here would be the El Laco magma chamber here. We've got a collapse, depressurization event. We have the eruption of this magnetite fluid suspension. And then on the surface, we have the texture that we see everywhere walking around at El Laco. So when you put it all together, it explains beautifully all of this magnetite at the surface. It explains all of the textures we see in the magnetite in the breccia pipes. It also explains the andesite enclaves, and it explains the class of magnetite here, because one of the things that we can say is that all of these andesite enclaves, they would be ripped up from the crystal mush here, and then during emplacement, we have all of that magmatic hydrothermal fluid that is the ore fluid carrying magnetite alpha beta crystallizing magnetite X and Y and Z and S. And that fluid can be responsible for the alteration of those andesite enclaves as we view them in the field. And that explosive event is what results in these complex textures that I'm showing you here on the right-hand side. So we've presented this now and gotten a lot of positive feedback. And some of that feedback was, it all sounds great, but can you actually demonstrate it happens at the appropriate pressure and temperature conditions for geologic systems? And the answer is yes. So the last bit of data that I'll show you today are from experiments that we conducted over the last couple of years, where the top here, this represents a capsule, where we've got the bottom of a capsule and the top of a capsule, and we're simulating a magma chamber. So if we go back to the cartoon on the lower left, we're simulating what happens to an andesite as it cools and decompresses. So we took an andesite, we heated it up to 1050 degrees at an oxidation state of nickel-nickel oxide +3, which is about FMQ +4, at 250 megapascals, which is about 6 kilometers. Oh, and one of the things I think I glossed over in a previous slide, that Broman et al. Study of the chlorine-rich fluid inclusions from Laco, their study indicated that those fluid inclusions were trapped at a pressure of about 100 MPa or a kilobar. So the fluid inclusions in their samples, which they sampled at the surface, were trapped at about 4 kilometers depth during the eruption of this magnetite fluid suspension. So we loaded the andesite with 6 weight% water, ±1 weight% chlorine. So we did some experiments with pure water and some with 1 weight% chlorine. And the results that I'm showing you here are what you would predict. Magnetite crystallizes, and then we've used red here just to train your eye to where the magnetite is. The magnetite, under a normal scenario, sinks to the bottom of the andesite, right? Magnetite's got a density of give or take 5. Andesite's got a density of give or take 3. Magnetite is more dense, and magnetite sinks after 3 days. But now look what happens when that same andesite is decompressed. So now what we're doing is we're simulating the volcanic eruption or collapse of the system at El Laco here, which results in a huge pressure change in the magma chamber, which essentially creates a vacuum to suck this magnetite fluid suspension to the surface. So focus your eyes top left first. We did the same experiments where we initially equilibrated the assemblage at 250 MPa, and then we decompressed it to 150 MPa at a specific rate of 0.025 megapascals per second, which is equal to a magma ascent rate of about 0.5 meters per second. And then after decompression from 250 to 150, we held it there for 72 hours. Now, what decompression does is it causes the andesitic melt to reach volatile saturation. So here, we only have andesite plus magnetite. Here, we have andesite plus magnetite plus bubbles. And notice that we get the reverse of what happened earlier. In this case, the top of the capsule is enriched in magnetite, and the bottom of the capsule is depleted in magnetite. So how in the world could you explain magnetite, a more dense phase than andesite, being at the top of the capsule? It just doesn't make sense until you look in detail. And this is a photomicrograph on the bottom right from this part of the experiment top left. And what you can see is, in this case, a magnetite bubble is wetting a cluster of small magnetite grains. And these magnetite grains are on the order of tens of microns. So they're not big hand-sized samples of magnetite. And all of these bubbles, when we did really careful image analysis through the upper portions of the experimental run product, we can see that all of the magnetite grains are in physical contact with these bubbles, and those bubbles float the magnetite to the top. So that after 72 hours, we go from left to right here, where we start out at 250 MPa for 3 days with no decompression. All the magnetite sinks. But then these 3 experiments that I'm showing you the results of on the right, F, G, and H, here we've got an experiment where we decompressed it from 250 to 150 MPa. We anneal it at 0 hours, and we see that magnetite is distributed within the andesitic melt, which is all of this orange glass here. We then anneal it for 3 hours after decompression, and we can already see a layer of magnetite. I mean, holy smokes, this is amazing. So now we've got the flotation of magnetite to the top of the magma chamber, and it forms this boundary layer here. And then if we anneal it for 72 hours, now we get a layer of magnetite that grows. So as a function of time, these bubbles are bringing magnetite up towards the top of the magma chamber. And imagine in the natural world where we have this increasingly thick layer of magnetite, magmatic hydrothermal fluid that's chlorine rich and also enriched in iron and sulfur and copper and other metals. All of a sudden now we have a collapse of the volcanic structure, and boom, we just pulled a vacuum and sucked that up to the surface. And that's how we formed El Laco. We've done lots of calculations, and please reach out to me if you want more details on these. But people have asked me, well, why do you need the suspension? Why do you need magnetite alpha and beta? Well, remember, magnetite alpha, it was originally titanomagnetite. It's now magnetite with ilmenite exsolution lamellae. You can't explain that magmatic hydrothermally. That has to have been original titanomagnetite crystallized from a silicate melt. And what we can do here is we've got magma chamber size on the y-axis. And if we have a magmatic hydrothermal ore fluid, and part of that ore fluid, 8% by mass, is igneous magnetite and alpha, then El Laco could form from a magma chamber size of about 50 cubic kilometers. Well, look at this. El Laco has a caldera diameter of 6 kilometers. So this is literally, this was the size of the magma chamber at El Laco. Everything just seems to fit. These are igneous magnetites, alpha and beta. We add 8% of those to an original magmatic hydrothermal ore fluid. So we've got 92% chlorine-rich fluid, 8% magnetite alpha beta. We have a caldera kilometer diameter of about 6 kilometers, which means we've got a volume of about 50 cubic kilometers, exactly what we know was the situation at El Laco prior to the formation of the ore deposits. And then importantly, notice the amount of FeO required from the magma or the melt. You don't need that much iron, right? You don't deplete the melt in iron. So if we source all of that iron from an andesitic melt, you only need about 0.5% FeO from the andesitic melt, and you get 375 million tons of iron, right? So it's amazing. Everything just seems to line up. So we put this story together, and we think everything fits. It satisfies and explains all of the stable isotope data, including now cap delta 17, hydrogen isotopes, oxygen conventional isotopes, iron isotopes. We have these beautiful cooling trends. High temperature magnetite alpha grows here at the bottom of the magma chamber. And then we, during collapse and essentially emplacement and eruption of the ore bodies, we get magnetite X and Y and Z and S. And you know, you look through the literature, and we also think this satisfies or explains the data from other systems. Here's a great paper a couple of years ago about Olympic Dam. They make similar observations of these magnetite-rich ore bodies at depth. We see also papers written on Karuna, and both of these papers here, Anne Westhus, who I think now is in Vancouver working maybe for the British Columbia Survey. You know, what Anne concluded in her studies of Karuna is that Karuna formed by magmatic hydrothermal processes. And we think that our model explains the formation of these ore bodies as the result of normal processes that occur during the evolution of magma bodies. And it's just that when all of the processes line up, you get these massive accumulations of magnetite. So then finally, again, I'd love to give a second talk on IOCGs. We see this now when we look at the data. These are lots of magnetite data from ore bodies all over Chile. We see the same cooling trends when we look at the trace element chemistry. Every one of these ore systems seems to behave similarly. We see the same thing with all of the stable isotopes. Here's iron versus oxygen. All of the systems we've looked at, they all plot within the magmatic high temperature field. And we've put this together in a way to explain the relationship between iron oxide apatite deposits and IOCGs, but I'll save that for a separate talk. And then last, I just want to give a shout out to a new podcast for those who haven't heard it. This is a podcast called Discovery to Recovery. And the latest episode, which I think is episode 4, has a great interview with Kathy Ehrig, who is the intellectual guru at Olympic Dam in Australia. And Kathy, in that interview, talks about a number of topics, including the massive accumulation of magnetite. And also, she uses the words magmatic hydrothermal to describe the formation of Olympic Dam. And we think that our model scaled up can explain Olympic Dam. And then last, apatite is also consistent, but remember, apatite is a side story. It's not even on the stage. And with that, I'll stop and be happy to take questions.